Hello, my name is Stephen Undy, and I'll be discussing Hewlett-Packard's newest PA-RISC processor, the PA-7100LC, or Hummingbird for short. Unlike previous PA-RISC implementations, Hummingbird had system design cost reduction as a top design goal. Because of this, Hummingbird represents the highest level of integration implemented to date by HP. Unlike the PA-7100, which it was leveraged from, it incorporates an on-chip memory controller, a reduced-cost cache architecture, and a second integer execution unit. As will be shown, this integration aids performance in addition to reducing costs. In this presentation, I will discuss the design goals for Hummingbird. I will give a brief overview of the processor. I will then discuss specific features that enable system cost reduction, high performance, scalability, power, reduction, and test. Finally, I will summarize a few key points. As I mentioned before, reducing system cost was a major design goal for Hummingbird. I would like to emphasize that system cost was reduced, not just component cost. In fact, some decisions were made to decrease system cost that actually increased the cost of the processor, the integrated memory controller being one example. Another key design goal was performance. It was important that the cost objectives did not compromise processing power. We wanted to enable meeting existing mid-range workstation performance levels in a reduced cost system. Like cost, performance was considered system-wide. Although Hummingbird has impressive integer and floating point performance, the chip also has features to support high-performance graphics and multimedia applications. These performance features were not added merely to boost spec mark ratings, but to produce real-world acceleration. Hummingbird is designed to be inherently scalable. This gives the customer easy upgrade paths, and it also allows HP to provide many price points in a number of different markets. Reducing processing power was another design goal. This, of course, reduces system cost. It also is an enabler for products in certain markets, such as those that cannot tolerate a large, noisy fan. It almost goes without saying that Hummingbird is completely compliant with the PA-RISC architecture. It is backward compatible with existing implementations. Hummingbird is also designed for manufacturing ease, mainly through the emphasis of testability features. The Hummingbird design took as its starting point the PA-7100. Many of its design features were used directly with little or no modification. They share the same 5-stage pipeline, branch prediction algorithm, and operand forwarding and interlock mechanisms. As I said earlier, Hummingbird is highly integrated. It incorporates a floating point execution unit, 2 integer execution units, a 1 kilobyte internal instruction cache, an external cache controller, and a memory and I/O controller. It is, of course, Superscaler. By adding a second integer unit, we made its instruction bundling capabilities more advanced than that of the PA-7100. In addition to being compliant with the PA-RISC architecture, Hummingbird incorporates several new extensions to that architecture. Hummingbird is dynamically switchable between big and little endian modes. It allows both big and little endian processes to run not only on the same machine, but to do so concurrently. The mixed endian ability greatly aids PC emulation, among other software. Hummingbird also allows uncached memory pages. This allows the speedup of certain classes of I/O drivers. The processor also supports a new class of arithmetic instructions that were specifically targeted for multimedia processing. Most multimedia applications will benefit from these instructions that operate on pixel, audio, and text data. These instructions provide addition and subtraction with saturation, arithmetic averaging, and support for multiplication by a constant. Hummingbird executes algorithms using these instructions up to 4 times faster than without them. Hummingbird is fabricated in HP's mature CMOS 26B process. This features 3 levels of metal interconnect and 0.8 micron gate widths. The chip operates up to 75 megahertz with margin. It contains over 900,000 transistors on a 14 millimeter square die, less than 87,000 of which are part of the internal cache array. It is packaged in a cost-reduced 432-pin, 1.8-inch square PGA. The package operates at high speeds without the need for bypass capacitors. The chip uses a 5-volt supply and has TTL-compatible I/O signal levels. This system diagram shows how Hummingbird is used to implement a low-cost computer system. The processor has 3 major ports, an external combined cache interface shown on the upper right, a dynamic main memory interface shown on the upper left, and a system bus shown at the bottom of the CPU. The external cache uses standard static RAMs, and the main memory uses standard DRAMs or SIMMs, all commercially available. The main memory interface has been designed to optionally control a set of address buffers for use with large memory arrays. The system bus connects to the I/O subsystem and to an optional bus converter, shown on the lower left. The system bus also connects to a specially designed graphics processor called Artist, shown on the lower right. The bus is a cost-reduced version of that used in HP's Snakes products, yet it still allows for high data transfer rates. This is a block diagram of the Hummingbird processor itself, showing the major data paths. There are 3 execution units, shown on the right side of this diagram, a floating point unit, and 2 integer units. The integer units are not identical. They both have ALUs, but one unit also contains a data shifter and a branch adder. The other contains a data operand address generation unit. Instructions are fed to the execution units from the first level instruction cache shown at the center top. The first level cache is connected to the external cache interface at the lower left. The cache interface in turn connects to the memory and I/O interface shown at the upper left. The cache interface also connects to the execution units to supply data operands. A 64-entry Unified Translation Look-Aside Buffer, or TLB, is used to map virtual addresses to real addresses and is shown at the center of this diagram. Hummingbird has a unique cache organization for a PA-RISC processor. To reduce pin count, a single external cache is used for both instructions and data. The data cache is organized as a single level structure, while the instruction cache is split into 2 levels, one internal and the other external. Note that the external cache is combined and that a single instruction can reference both the instruction and data caches. Because of this, the first level instruction cache was added to prevent pipeline stalls. Whenever the external cache is not used to reference data, instructions are prefetched from it to the first level cache. Because the TLB is also used for both instruction and data translation, a special register contains the current instruction real page number. This register only needs to be updated from the TLB whenever an instruction page cross occurs. This is a photograph of the Hummingbird Die. On the left bottom, on the right side of the chip along the bottom is the integer data path. Along the left side towards the bottom is the floating point data path. In the center of the chip at the bottom, you can see the level 1 instruction cache. The memory interface is at the upper left of the chip, and the cache interface is distributed throughout the I/O ring of this chip. In 1989, the first CMOS implementation of the PA-RISC architecture required 9 VLSI parts to implement the processor, cache controllers, system interface, and memory controller. In 1991, this was reduced to 3 parts: the core CPU, a floating point unit, and the system interface memory controller. In 1992, with the PA-7100, the floating point unit was integrated onto a single processor chip. Now, with Hummingbird, all of this functionality sits on a single piece of silicon. Obviously, the integration seen on the previous slide is a major enabler for low-cost system design. The biggest change from previous processor designs was the integration of the memory and I/O controller, but other design choices were also made to reduce system cost. Both the DRAMs and SRAMs connect directly to Hummingbird with no other buffers or glue logic required. SIMM parts are also directly supported. These memory parts are standard and commercially available, reducing design and manufacturing costs. The entire cache requires only 12 static RAMs using by-8 technology. The cache system is designed to utilize as much bandwidth as possible out of a given SRAM part. For example, 12 nanosecond parts can be used in a system that runs up to 66 megahertz. Another area that reduced system cost was the low-power design techniques used in Hummingbird. I will discuss this in more detail later. The IC process used to fabricate Hummingbird is stable and mature, allowing for low manufacturing costs. In addition, the packaging used is one of the lowest cost design for a PA-RISC processor. To reduce chip active area, the floating point multiplier array was reduced in size. This was done in such a way as to not affect single precision performance. Control area was reduced by not optimizing divides and square roots as much as was done in the PA-7100. The TLB was reduced from 120 entries in the PA-7100 to 64 entries. The TLB is unified, saving the need for both a data TLB and a more rarely used instruction TLB. The decision to add specialized multimedia instructions to Hummingbird allows multimedia algorithms to be accelerated without the need for more expensive, dedicated hardware. Hummingbird can launch instructions on 2 of its 3 execution units every cycle. 3 instruction classes are defined. Class A consists of integer ALU instructions, shift merge instructions, and branches. Class L consists of loads and store instructions, both integer and floating point. Class E consists of all non-memory floating point instructions. Hummingbird will launch in parallel or bundle a pair of instructions if they are from different instruction classes or if they are both integer ALU instructions. In addition, pairs of integer loads or stores will bundle if they are to the same double word address. There are no instruction alignment constraints for bundling. Register dependency checking is done at the time instruction bundles are launched. The floating point hardware, although subject to some cost reductions, still achieves high performance levels. This table shows floating point latencies and issue rates for various operations. Like the PA-7100, adds and subtracts can be issued every cycle for both single and double precision and require 2 cycles to complete. Single precision multiplies and compound operations using the multiplier have the same issue rate and latency, while double precision multiplies are slightly slower. Divides and square roots take 8 cycles for single precision and 15 cycles for double precision and are not pipelined. Hummingbird incorporates several features to enhance virtual memory performance. In addition to the 64 entries in the TLB that each map one 4 kilobyte page, there are 8 block TLB entries that can map 512K through 64 megabytes. The TLB is fully associative. The processor implements a TLB mishandler directly in hardware that reads the page table without trapping the software. In the event the TLB miss does trap the software, 2 features decrease the software miss penalty. Hummingbird implements instructions to perform a fast insert of TLB entries without having to explicitly read the parameter registers. Secondly, a subset of the general registers is saved upon trapping and automatically restored upon return. Hummingbird has a high-performance cache system. The external cache runs at the processor frequency. This means that loads execute with no pipeline stalls. Store instructions need to perform a write of the external cache, which requires 2 cycles. The extra latency to perform a store is hidden if the subsequent instruction bundle does not reference the cache. In addition, the stores are pipelined such that one store will read the cache tags while another is updating the cache data. The external cache is virtually addressed, and a hashing function is used to form the cache address to prevent thrashing. Several features were included to optimize cache miss performance. On an instruction miss, the instructions returned from the memory controller are executed as they are delivered and written to the caches. On data cache misses caused by loads, the CPU pipeline will not stall until the target of the load instruction is referenced. The cache can be referenced without penalty during the latency of a data cache miss and between cache move-in cycles. During a store miss, subsequent stores to that same cache line are executed without penalty. During a data cache miss, if another cache miss is detected, the pipeline will stall, but the second miss address is accepted by the memory controller before the first miss ends. This allows the memory controller to optimize the DRAM references. A block copy hint can be specified on stores that prevents a move-in from occurring in the event of a cache miss. This is useful when a large block of data is to be written. Another hint may be specified on semaphore instructions to allow the semaphore operation to be performed directly in cache without referencing main memory. Hummingbird also incorporates aggressive instruction prefetching. Prefetching occurs at 2 levels on the processor. A main memory prefetch occurs whenever an instruction miss is handled by the memory controller. In addition to fetching the missing line, the following line is fetched and held in the memory prefetch buffer, shown here in the upper left. If the next instruction miss hits this buffer, the data from this buffer is sent at the maximum cache move-in rate. The other prefetching takes place between the external and internal instruction caches shown on the right. A pair of instructions is read from the external cache whenever it is not being used for a data reference and placed into a 2-entry prefetch queue. A pair of instructions can be written from the queue into the internal cache every cycle. The internal cache can be both read and written on the same cycle with no waits. Instructions can be bypassed out of the prefetch buffer without penalty. In addition, if an internal cache miss is detected while a prefetch for that instruction is in progress, the internal cache miss penalty is reduced in half. Lastly, whenever a predicted branch is executed, the external cache automatically prefetches the branch target. As I mentioned before, the memory controller has a dedicated 64-bit DRAM interface. The Hummingbird processor takes advantage of the tight coupling that exists between the CPU and the memory and I/O controller. To reduce latency, the cache issues addresses to the memory controller before a cache miss is even detected. Also, the critical double word on a cache miss is always sent first. Through these techniques and others, latency on a data cache miss is just 7 CPU cycles. The memory controller utilizes the fast page mode of the DRAMs whenever possible. This greatly helps data transfer bandwidths. The memory controller also can utilize extended data out capabilities of DRAMs that support it, leading to high data rates, especially for higher frequency systems. I/O performance is aided by having a dedicated 32-bit system bus capable of sustained DMA rates of 120 megabytes per second. In addition, the CPU is not blocked from memory when DMA transactions are occurring. Together with the high-performance memory and cache algorithms, the I/O system is capable of 50 megabytes per second of CPU-controlled memory to I/O transfers. This is especially useful for high-bandwidth I/O devices without a DMA controller, such as graphics processors. Hummingbird is very scalable. It was designed to run from DC to 75 megahertz. It's worth mentioning that HP has had little difficulty in pushing PA-RISC processors to higher frequencies when the need has arisen. PA-RISC defines and Hummingbird supports a 48-bit virtual address space. The external cache can range from 8 kilobytes to 2 megabytes. Main memory can range from 4 megabytes to 2 gigabytes. The memory controller can be programmed for a variety of DRAM, latencies, and timings. Finally, the system bus can run at either 2-to-1 or 3-to-1 ratios with the CPU frequency. This inherent scalability means that not only does Hummingbird enable a very low-cost system with high performance, it also enables systems with very high performance at a moderate cost. The Hummingbird processor is one of the lowest power PA-RISC implementations, less than half the power of just the PA-7100 CPU alone. This was achieved by limiting the use of dynamic circuits, replacing power-hungry programmable logic arrays with fully static circuits, powering up the TOB, floating point megacells, and the register files only when needed, and by utilizing gated, not-overlapping clock nets instead of high fan-out set and dump lines. Hummingbird incorporates several features to enhance testability. This in turn reduces manufacturing and design costs. These features include a JTAG-compliant test interface, the ability to perform serial and parallel block tests, extensive scannability, the capability to perform single clock steps, and circuit designs that fully support IDDQ static current testing. I've demonstrated that Hummingbird has met the design goals set out for it. It has been optimized for low-cost systems while still providing high performance. It is configurable from entry-level systems up to higher-end systems while not sacrificing its price-performance advantages. It incorporates a number of new features that increase processing power, especially for multimedia applications. It is low power and inexpensive to manufacture. These combinations of features promises to make it one of HP's most successful processors. Thank you.